In our continuing tutorial sequence on plane waves at interfaces, we're now ready to handle part 2 of the mathematics of how the electric field behaves at the boundary. So what we set up so far is that the total electric field in space is equal to the sum of two expressions. One is an electric field in region 1 on the left-hand side of the boundary, and the way we enforce it being the left-hand side is this step function. And we have a similar expression on the right-hand side, a plane wave in material with refractive index n2 and an appropriate step function there. Now what we want to do is take the divergence of this electric field. This is first of Maxwell's four equations. So the question is, what's the divergence of this electric field? Homework for this class is going to involve evaluating the other three expressions, but we are going to do the first one here. So the first thing to do in taking the divergence of this expression is to notice that we have products of a scalar, the step function, and a vector, the plane wave. Let's take advantage of the way product rules work for a scalar and a vector. So the divergence of scalar times vector equals scalar times the divergence of the vector plus vector dotted into the gradient of the scalar. We saw in the previous tutorial, but I will recount here without proof, that the gradient of the step function is equal to a unit vector times a delta function. I'm going to first evaluate this del.fg expression using the step function as my f and the plane wave as my g. So I'll set up a big brace here. So first f times divergence of g, that's going to be the step function, times the divergence of e, the divergence in this case of E1. Now right away we know something useful, because remember, this expression, if you go back in previous tutorials, is the expression for a plane wave propagating in an infinite material of refractive index n1. There's simply no divergence for that electric field. There's no place where charges build up within the volume of the material refractive index n1. So this expression immediately vanishes. What's the second term going to look like? So that's going to be g dot grad f. So the electric field E1 dotted into the grad of f. Now this is the negative step function. The only way that its gradient changes is that there's still a delta function at the origin, but it's a negative delta function. So we can put that negative into the unit vector and say it's the dot product with negative x hat and then the delta function. We now, of course, have to add on what's happening to this guy. The result is very similar. Now our f function is the positive step function. We have the divergence of E2 instead of E1. But E2 also is a plane wave in a uniform, written for a uniform material with refractive index E2. No charge builds up anywhere in that material. So also the divergence of this expression has to be 0, because no charge density would build up if it were just an infinite material of refractive index n2. And we add to that a corresponding expression E2. Now in this case we're going to have a dot product with positive x hat, but exactly the same delta function. So this is the expression for the divergence of the electric field. And it's got to be equal, this whole thing, by definition, has got to be equal to the charge density per unit volume over epsilon naught. These two end expressions are, of course, Maxwell's first law. Now we have a situation where there's no free charge anywhere. As we discussed earlier in the course, the only charges that are unbalanced anywhere in space are due to the dielectric polarization of each material. And as discussed in the previous tutorial, there really will be unbalanced charge built up at the interface due to the fact that the two materials don't polarize the same way. Well, there's another fact that we know from earlier in the course, which is that the charge density due to polarization is mathematically given by the negative gradient of the polarization. If you substitute in this relationship for rho polarization here, you get that what we're doing is taking the negative divergence of, and I'll write it as polarization over epsilon naught, and then we bring in the fact that polarization over epsilon naught is related to the susceptibility of the material. P over epsilon naught, you may recall, is equal to chi times the electric field. That was in fact how we originally defined refractive index in terms of susceptibility, was that depending how susceptible the material is, it will polarize more for the same applied electric field, which leads to a greater refractive index. Let's simply follow what's going on this side now. We've got the E1 dotted into negative x hat vector. We can call that by the name E1x, as mentioned in the previous tutorial. It's the component electric field pointing towards the interface, and that's going to be negative. E2 dot x hat is going to be positive, and both of these two terms are multiplying the delta function. The divergence of the electric field is apparently going to be 0 everywhere in space except right at the plane x equals 0, which is right. But at the plane x equals 0, the divergence isn't necessarily 0 because these two electric fields aren't necessarily the same in their x components. What do I get on the right-hand side? Well, the divergence of E is what led to this expression with subscripts 2 and 1 and a delta function. The divergence of chi E, it's going to have exactly the same format of having a 2 term and a 1 term. So in this case, there's an overall minus sign, which there wasn't on this side, so it's going to be the E2 term that has a minus and E1 term that has a plus. So it's going to be chi 1, positive chi 1 E1x minus chi 2 E2x. Times the delta function. So by having analyzed the divergence of E, we can very quickly write down by inspection what the negative divergence of chi E is equal to. We simply take the term on each side of the boundary and write it down as we had it here. Well, if you just group terms here, I'm going to get E2, if I bring the E2s onto the left, I'm going to have E2x times 1 and then plus chi 2, because it's a minus on the other side. And for E1, if I bring both terms together, the negative E1 on that side becomes, how much E1 x on this side do I have? The negative E1x comes over here and becomes positive 1. And then I've got a positive chi 1 here. I've got a delta function on both sides of the equation, so I can actually just look at those two guys and say that when I'm at x equals 0, so they cancel out, and at x equals 0, this expression now must be true. Away from x equals 0, these terms don't have to equal each other because the delta functions go to 0, satisfying this equation. But at x equals 0, where the delta function is non-zero, it must be that these coefficients balance each other. And if we just follow the math forwards on that, we've got one more interesting fact, which is that 1 plus chi 2, well, that's the definition of N2 squared. That's our definition of refractive index for a plane wave. Same thing here. This is going to give us N1 quantity squared. And so therefore, the mathematical end result is that there is a relationship between E2x If I bring n2 squared onto this side of the equation, I get that it's equal to a ratio of n1 over n2 squared times e1x. And if I just quickly draw an interface and talk, as in the previous tutorial, about the electric fields E1x pointing this way, E2x pointing this way, to get away from being specifically attached to calling them x's, if I just call this E1 perpendicular to the interface and E2 perpendicular to the interface, I could simply rewrite the expression in a final, more universal form, that the perpendicular to the interface component of E2 is equal to the ratio of the refractive indices squared times the left-hand side's electric field component perpendicular to the interface. This then represents one of Maxwell's four equations in differential form evaluated at a boundary. The other three will be evaluated by you, the student. It turns out that this is the most complicated of the four, but they all follow this general form of evaluating either a divergence or a curl, which is the product of a step function times a vector field, and following your nose until you get to an expression like this.